wise and all that?
Yep, you both are good to go.
All right, great. All right, everyone. I am here with Pablo Samuel Castro. Pablo is a staff research software developer with Google Brain, and we are here for our annual AI Rewind 2020 session with a focus on reinforcement learning. Pablo, welcome back to the TWiML AI podcast.
Thank you for having me back. It's always a pleasure.
It is my pleasure, and I'm looking forward to this session. You have done a lot of homework and pulled together a lot of papers for us to talk through. For those who have not heard one of our AI Rewind shows before, this is maybe our third year doing them, and the idea is to check in with folks who have been on the show generally previously and kind of take their temperatures in terms of what they think are the big developments in their field of research. And for Pablo, that is reinforcement learning. So maybe, Pablo, we can start with having you kind of share kind of broad brush reflections on RL in 2020. 2020 itself was a crazy year in so many ways. Did that translate to RL?
Yeah, I mean, it was a pretty wild year in so many respects. I think they're mostly negative, unfortunately, but it's still heartening to see that despite all these challenges, there's exciting things happening in the RL world and just in the academic community and beyond. There were some really great things that came out of this year. I think the realization that things can happen even if you're not physically in the same space, I think opened up a lot of doors for new technologies, for what it means to hold a conference, what it means to hold an inclusive conference. Obviously, I still prefer physical conferences, but I think the fact that we were forced to have these virtual conferences meant a lot more people could participate from all time zones and all over the world without restrictions of visas or budget or anything like that. So I think that was quite a positive thing. And also for me personally, it was I live in a different city from where my office is, so being forced to work completely from home made me realize that I can still be quite productive even if I'm completely remote. I mean, I guess other people realize this as well. I know it wasn't the same for everyone, but I already had a bit of momentum working from home, so it was pretty good. In terms of RL, I think there were a lot of really exciting developments this year. I mean, the field continues to push forward. One of the things, or two things actually, that I kind of feel in the air and I'm very excited about happening is one is we're starting to see reinforcement learning being used in the real world beyond gaming situations. Mm-hmm. That's one of the papers that I published with my collaborators this year that we can talk about later. But that is something that I think is indicative, I think, of what we'll start to see more and more, that are going beyond gaming benchmarks or benchmarks that are restricted to research labs and really being used, put to good use in the real world. The other is, I mean, this has already been happening for a while, but I feel maybe it's perhaps just my own interest is growing more, but I feel like there's more interest and emphasis in really trying to understand what is happening when you combine deep networks with reinforcement learning. I think a lot of us that grew up with reinforcement learning before deep networks, we sort of learned to love all the theory that came with it up to linear function approximation. And then and it's still kind of the case that most of the theory that is produced, it stops at linear function approximation. And then beyond that, you kind of base yourself on the theory and you have sort of good best practices and things like that. But there's still a lot we don't know. And there's a lot of brittleness in terms of how you combine things and a lot of unknowns. And I think we're starting to see more and more papers can bring a magnifying glass to those design details. And this is really exciting because, again, it goes well with this idea of using RL in the real world. I mean, before deploying things in the real world that can have like real life effects, you really want to be sure of what's happening. And I think doing these types of empirical and scientific analyses will help us get a better grasp on that.
Mm-hmm. How much of that is very deep RL specific? I know the same impetus to better understand deep learning in general has been, ongoing for the past few years. Are the breakthroughs that you're thinking about, or the progress that you're referencing, is deep RL specific?
Yeah, so I think there has been quite a bit of work to understand deep networks in the supervised or unsupervised setting, and a lot of it does translate to reinforcement learning, but a lot of it doesn't. And the reason for this is that in most cases, when you're dealing with something like supervised learning, you have a fixed data set, right? And so you're sampling from this fixed data set or from a distribution that's known beforehand. With reinforcement learning, it's quite different because you're typically, in traditional reinforcement learning, you're interacting with an environment, and it's through your interactions that you accumulate experience, and that experience is what you use to learn and improve your behavior. But how you collect that experience is a direct consequence of your behavior policy, and how you improve that behavior policy is obviously affected by your algorithm, but also affected by how you collected that data. And so there is some work in what's called offline or batch RL, where you don't get to interact with the environment. You're handed a chunk of data, and you have to do your best with that. I think that's quite interesting work and a quite interesting field. There's been a lot of work in that space as well in this year. And the reason I like it is because it helps disentangle this idea of the shifting distribution of data, and how if you have a fixed distribution of data, then you can focus on some of the other components of reinforcement learning. The other aspect that makes reinforcement learning quite challenging is this issue. I mean, it's part of the deadly triad that's well known, this issue of the bootstrapping, where you're basically building estimates using your previous estimates. So if your data distribution kind of goes wrong along the way at some point, that could potentially lead you down a wrong path that's hard to recover from. And so we have theory for how to deal with these things, but again, these theories typically stop at the linear function approximator setting. And so I think this is what makes this idea of understanding deep networks quite challenging in the reinforcement learning case, because we have it's a dynamical system, and the training data that we have, you can almost view it as a completely dynamical system. And so that makes it really, really challenging to get a firm grasp on, in particular, theoretically, if you want to get a theoretical grasp on these things.
Mm-hmm. Mm-hmm. So you have pulled together a ton of papers for us to talk about, and they fall into several categories that you think are, areas that we've made some interesting progress in this year, or that have been a focus for the community this year. Let's maybe start by talking about the different categories that you're excited about, and then we can dig a little bit deeper.
Sure. So these are definitely not exhaustive. So there's many other areas of research that happened in 2020 that is very exciting. So this is by no means, if something isn't here, it doesn't mean that it didn't happen or that it's not exciting. It's more that it's not an area I'm particularly active in. So I'm not doing a ton of research in that space, and that I'm not, perhaps don't have as much background knowledge as some of the areas that I'll be talking about here. I mean, as you've probably inferred, RL has grown a ton in the past years. The Deep RL workshop is basically a conference in itself. It's huge, and so it's really hard. It's becoming hard to kind of have a good grasp on what's happening across the whole field. And so inevitably, I'm going to be omitting things, and rather than trying to do a shallow survey of what's happening, I wanted to kind of focus on certain areas that are the areas that I'm most excited about. So yeah, I grouped them into 3 or 4, categories. So the first one I called representations or metrics, but you can also think of generalization falling in this space. And here, this is again, in particular with the case of deep RL, where what we're trying to do, part of the draw of deep networks is that they're able to generalize well, right? So in the pre-linear function approximator, when you're dealing with a tabular setting, so that has some advantages, but it doesn't really generalize that well because every state has its own prediction and its own approximation, and so that doesn't naturally carry over to other states. With deep networks, one of the advantages of it is that when we update for a particular some estimate for a particular state, because the parameters are shared in this network, we end up updating for nearby states. And so that's where the idea of representations comes in, that you want to learn a good representation such that all the states affected by an update are actually states that should be updated by whatever learning process you're doing, because otherwise you end up moving things that you don't want, and it becomes more difficult to do to learn in that setting. And so I think there's a lot of types of papers that are related in the space. So there's papers that cleanly fall into representation learning and even call it that way in their titles. There are other papers that are dealing more with generalization, but I think they kind of fall into the same bucket in the sense that you're leveraging past experience for unseen experience. And I threw in metrics in there because this is an active area of research for me. This is perhaps the smallest of the three that I mentioned in this category, but the reason I put it in here is, well, one, it's a very active area of research for me, but also I find there's a lot of theoretical basis for what it means to have a good representation when you're talking about state metrics or state action metrics. And there has been some work for the past 20 years on this area, where if you can have states that have a distance between them that goes beyond like physical proximity, it's more like a behavioral distance, then having these sort of grouped together in your representation space will likely lead to better representations. So that's one grouping. The second grouping that I came up with is what I was just mentioning before. So understanding or evaluating deep reinforcement learning in a deeper or more principled way to get greater understanding for what's happening and really sort of poking holes at all the unquestioned assumptions that we often carry over from just kind of get grandfathered in as you build on top of previous algorithms. Mm-hmm. So that's another category. Then I also have reinforcement learning in the real world, which is something I mentioned a little while ago, that we're starting to see a bit more of this in 2020. And then finally, I have an other category, and these are just a couple papers that I found neat and particularly exciting for different reasons. We can talk about them later.
All right, cool. Well, let's dig into the generalization topic. In terms of representations, one of the topics that was on my radar quite a bit end of last year and throughout this year has been this whole idea of model-based reinforcement learning. Is that a big part of that category that you mentioned?
Yeah. So there's a big chunk of papers, and there's been quite a number of papers in this year that are dealing with these latent models or world models, mm-hmm. where you essentially learn a latent representation that is, or they try to learn it in a way that it's reflective of the real environment. And so the advantage of that is that you basically end up learning a model of the world. And so mm-hmm. if you have a model of the world, then you can learn on that model without having to interact with the environment itself. And so how you learn that model of the world is obviously where the challenge and where the research lies. And so a lot of the work in that space has focused mostly on pixel-based environments, where you have images. And that's understandable. A lot of our benchmarks are built on this. So Atari video games, yeah, exactly. DM Lab and those things like that. But also, I think a lot of the work, for instance, a lot of these works use things like VAEs for learning these latent representations, and VAEs are traditionally used on images, and so there's the way you train them is quite well understood in the image domain. And I think that's another one of, there's work already in the non-RL deep network setting, but VAEs are not easy to train. So you read about them, you understand them, and then when you start training them, there's a lot of tricks that you kind of need to know, or need to have somebody tell you so that they can train properly.
I think I've seen at least one long Twitter thread on VAE training tricks this year.
Yeah, so there was one paper that came out. Was it ICML? I can't remember. It was like a month ago or something, and I remember looking through it, and there were just all these little tricks that you had to do. And coincidentally, at that time, I was working on a VAE for a particular project I'm working on, and sort of rediscovering these tricks. So, you code up your VAE and you throw your data at it, and it's like, okay, it doesn't work. Now it doesn't work. Okay, well, let's normalize the data. Okay, sure. Yeah. That makes sense after you think about it, but it's not something that, that it doesn't come with the instructions right. When you bought your VAE. And so, but that obviously has a huge effect. And so normalizing the data has a big effect. And then there's a whole collection of tricks that people use to get these things to train properly. And so to come back to the original point of pixel-based domains, I think probably that has something to do with it. Like if you're trying to train these autoencoders where there's quite a bit of knowledge and experience in training them for image domains, then it makes sense that you want to start with those types of domains, which are also the ones kind of most welcomed by the research community, or that are very welcomed by the research community. So yeah, there's quite a bit of work. Let me highlight a couple papers. So I collected a bunch, but I didn't necessarily put them in great order. So there's the and these again are not in any particular order. I took these papers from the proceedings of ICML, NeurIPS, and iClear from this year. I did that because I wanted to sort of focus on peer-reviewed papers. If I go through archive, the list would have been 1,000 times longer. There's a lot of interesting papers there, but just to sort of set some rules, I decided to focus on these. So the first paper was an iClear paper. It's called Contrastive Learning of Structured World Models by Thomas Kipf, Elise van der Poel, and Max Welling. And so here, they're basically combining this idea of learning these world models, but also with some structural inductive biases. So in particular, the biases that they're looking at is assuming there's a collection of objects in your environment that interact in some particular way. And so they're using graph neural networks to sort of learn the relationships between these objects. And so if you say there's 5 objects in my domain, then their architecture kind of learns to figure out how to map the different pixels into different object categories, and then how to sort of connect them via this graph neural network. And I thought that was quite interesting. I think a lot of people often look down on papers that are injecting these types of inductive biases because it's like, well, it's not general enough. Sure, but again, coming back to the question of the real world scenarios, when you want something that works in the real world, you're going to have to inject domain expertise into it. Like a completely general purpose algorithm is likely not going to perform very well. And so understanding how these different inductive biases work is I think, quite important. One thing that this paper highlights that I think is true for a lot, if not most, of these world model type papers is that they assume deterministic transitions. And so dealing with stochastic transitions is obviously much more complex. And it's a simplifying assumption that I've taken myself in one of the papers that I'll discuss later. But it's a reasonably strong assumption still, especially if you're trying to say something theoretically about these methods.
What's the role of the transitions in this paper? The setup, as I understood it from your brief introduction, was I'm imagining a static scene with some fixed number of objects. Mm-hmm. Where does the transitions come into play?
It's in the graph neural network. So that graph neural network kind of encodes the transition model. Mm-hmm. So I guess it's important for them to have deterministic transitions, because if you have an action that says, for instance, push this object left or something like that, then it will go left. It's not like it might slip and stay where it is. And so I think I'm not sure if they actually tried it with stochastic transitions or not. But a lot of these papers, even though they end up demonstrating their efficacy with experiments, a lot of them do have like some theoretical foundation to them. And often, this is the case with my AAA paper that I'll mention later. But often the theoretical results require the determinism assumption. Otherwise, things kind of can break down.
Yeah, I'm not sure that it's quite the same, but you were just tweeting about deterministic rewards versus random rewards, weren't you?
Yeah. Yes. It's related. Related to my AAA paper. I'm still working on that stuff, and I can talk about that a little bit later.
Okay.
Once we get into the metrics side of things. So another paper that I quite enjoyed is curl. This was, I think, an ICML paper, and so curl stands for Contrastive Unsupervised Representations for Reinforcement Learning. Michael Askin, Aravind Srinivas, and Peter Abil. So a lot of these works use what's called a contrastive loss. Mm-hmm. So contrastive loss is you can think of it as you have some sort of measure of whether things should be close or far, and if they're close, then so you have positive and negative examples. So positive examples, you want them to be close. Negative examples, you want to be far away. And so how you figure out what's positive and what's negative, it varies from paper to paper. So some papers will do things like they'll apply some type of data augmentation to your pixel. And so you want the images that have been augmented, you want them to be kind of close to the original so that it's robust to these types of perturbations. Other papers will for instance, say any states that are within like 3 steps or something of the original state, we want them to be close together because they're sort of nearby in this dynamics model. And other papers will use things like metrics, like this is the work that I'm using. So you have some type of behavioral metric that tells you these states are close, these states are far. And so you can use them using thresholding or just use the metric directly. But essentially what you're trying to do is, with these contrastive losses, is push together state representations that are nearby and push apart state representations that are not. Mm-hmm. So again, with these contrastive losses, there's also tricks that you get to learn as you play with them. So for instance, cosine distance is a very popular distance function to use for these losses. If you use something like L2 distance, it tends to not work quite as well.
Okay.
So anyway, curl is one of these papers that uses contrastive losses. And so they have this architecture that's, I guess it's sort of inspired by LSTMs or this type of thing where you have queries and keys. And so you do some data augmentation based on your observations. And so some of these become your query observations, which you feed through an encoder. And then you have key observations that get fed through another encoder. And so they use them in this kind of funky way where the query encoder is that's all that's used for the control. So basically for choosing actions for your RL agent, and then the query and the key encoded representations are then combined into this contrastive loss. And so you have these two loss functions. One is the typical RL loss, and then the other is the contrastive loss. And it seems to produce some pretty good results.
So the general idea there is that the contrastive loss provides an additional constraint that helps with generalization in some way.
Exactly. So this is coming back to what I mentioned initially, where you want to have states that map to a representation that's nearby. If those states sort of share some type of property or quality, right? So typically what we're interested in is value functions, because that's, or Q values, because that's how we're, in value-based methods, that's how we're picking actions, right? So if you pick, you want to make sure that when you map states together, that they'll have the same optimal action.
Right.
And this will come back later. Sorry?
Those Q values are, you can think of those as more, domain or problem specific and less about the representation, and the contrastive loss is a way to also optimize the representation. Is that?
Well, it depends. So here, again, it varies on what you want to do. So if you want to do single shot learning, where you want an agent that will get thrown into a task and it'll learn quickly there, then really what you care about is Q, how Q evolves. And you want to make sure that states that are nearby together for your current instance of Q, that they sort of share the ordering, at least, of Qs, so that you don't make mistakes when choosing actions. But if you're really interested in generalization and you want something that's more like reward agnostic, say, or something that will be robust to sampling different transition dynamics or different reward dynamics from an underlying distribution, then you definitely need something more than Q. And that's where it's important to figure out like what is going to be this notion of proximity that you use in your contrastive loss. Mm-hmm. And this is where metrics, I find, can be really useful, and I find them really exciting, because these metrics are built up theoretically, and we can prove theorems about them that strong theorems that say what they capture about what properties they capture about the two underlying states. So, I mean, maybe we can go into metrics now. This is kind of a natural segue, and we can. So what I'm going to do is, this was by the way, a small parenthesis. Compiling these papers was a great exercise. I'd never done something like this, like at the end of the year. Sort of. So this was great. I enjoyed it. So I'm going to probably put a post on my website with all these papers. So even if we don't go through all of them, then maybe you can put a link to it or something, so people can go check out the other papers that we weren't able to go over. Cool. So to come back to the metrics idea, the reason I like these metrics is exactly for this reason, that you can build them up from a strong theoretical foundation. You can prove things about what it means for two states to have a distance of 0 or a distance near 0. And then you can incorporate these perhaps in a contrastive loss to try to get better generalization or better representations or whatever it is you're trying to do. Mm-hmm. So one of the metrics that I've been working on since my master's back in 2005 are these things called by simulation metrics. And so these metrics, they come from concurrency theory and formal verification, where so in that type of literature, often what you'd want to do is you, in formal verification, you have a real system that has some type of specification for it, some logical specification for it. And so you want to be able to guarantee, for instance, that this system will never crash your rocket ship or something like that. And the way you do this is via something like linear temporal logic or something like that. And so if you can state a formula in linear temporal logic that says this system will never crash your rocket, and you can prove that it satisfies that statement, then that's great. Then you can sell it with with confidence. So simulation basically is a theory that started looking at when you have a logical specification, is it a proper simulation of the real system? And the way it was developed is via a series of tests, right? So you can do tests and sort of run them in tandem, the real world and the real system and your logical specification. And if you find a discrepancy, then obviously your logical specification is not a faithful simulation. So it was very one-sided in the sense that system A simulated system B. And then they started looking at bi-simulation, which is basically two systems that kind of simulate each other, in the sense that if you're placed somewhere in system A and you have an adversary in system B, the adversary is going to try to make you realize what system you're in. But if these systems are truly bisimilar, there's no set of actions that the adversary can take that will distinguish between them. So they're really indistinguishable. And so that's kind of the original idea for bisimulation, and they developed metrics for them and all of these types of things. But it was really not, at that time, not meant for Markov decision processes. And so in 2004, my PhD supervisor, Prakash, and Doina Prikop, they were both my PhD supervisors with Norm Ferns, developed bisimulation metrics, which kind of took that idea and brought it into Markov decision processes. And so in a nutshell, what it's essentially capturing is it's saying two states are bisimilar if they agree on immediate reward under all actions, and they also transition with equal probability under any action to bisimulation equivalence classes. So it has a kind of circular definition to it in the sense that I talked about bisimulation equivalence classes in the definition of bisimulation. But this is all well-defined and there's a whole theory behind it. But essentially what it's saying is, let's say an oracle gives you bisimulation and now you just group together all states that are bisimilar. This system is indistinguishable from the original MDP. And so what this means is that you can do things like state aggregation, right? So if you have a lot of states that group together, then you really don't have to think of all of them separately. You can just think of them as one aggregate state. And so when you extend this to metrics, where now it's no longer binary, like are you bisimilar or not, but how close are you? If you have a distance of 0, then you're exactly bisimilar. The closer you are to 0, the closer you are to being bisimilar. What's nice about this distance is that it upper bounds the difference in optimal values between these two states, right? So if you have a state S and T, and they have a bisimulation distance of epsilon, then that means that their optimal values will differ by no more than epsilon. And so when we come back to representation, this is great, right? Because this is exactly what we were trying to say, right? We want states to get grouped together when they share a particular property. So if you think of approximation error and you're sort of, whenever you move state S, state T also moves. Because of this theory, you kind of are guaranteed that it won't really change by more than epsilon. So that's a very high level. There's a lot of theory that goes into this, but maybe I can start going into some of the papers in this space that I'm particularly excited about. One that we presented. Sorry,
are all of the papers relying on the same idea of similarity, or are there different expressions of similar ideas?
Yeah, so all of my papers are based on bisimulation metrics, not surprisingly, but there's other notions of distance. So let me go through a couple. So the first one I have here is this paper that was at iClear, Dynamical Distance Learning for Semi-Supervised and Unsupervised Skill Discovery by Christian Hartikainen, Qinyang Zheng, Thomas Harnosha, and Sergey Levin. I probably mispronounced all of those names. But here what they're looking at is distances to particular states. So this is very goal-oriented RL in the sense of, like if you're in a state S, how far is state S prime from you? Not in terms of Euclidean distance, but in terms of transition dynamics. Mm-hmm. And so there's quite a lot of work with these types of ideas. I mean, some of the options work also sort of relates to this, where you're really thinking trying to summarize, if I'm in this state, how long does it take me to get to this other state or this other state? And perhaps you can incorporate that into planning. Or if you have two states that are sort of equidistant from the same goal state, then maybe they're similar in some way. So this is just to highlight that not all papers are looking at by simulation metrics. Mm-hmm. But some of these notions, I think it becomes somewhat more difficult in the general setting to say something about value functions. So in this case, they're restricting themselves to sort of goal-oriented MDPs. So there, if you have certain restrictions, like sparse rewards, and you only get a reward at the goal, something like that, then the metric you get might be able to tell you something about what you're doing. One paper that's quite a bit more theoretical, but maybe I'll come back to that later because it's not as close to metrics, which is what we're talking about right now. So another similar idea, and I don't know if this is really a metric, but it's this idea of sort of aligning states that are similar in some way. Is this paper called State Alignment-Based Imitation Learning, and this was in iClear as well, by Fangxin Liu, Sanling, Tongsu Mo, and Hao Su. And here, this is the framework is imitation learning. So you have an expert, and you have expert trajectories. And so what they're trying to do is learn some latent space. So they're using a VAE again for this. Some latent space where the states that are sort of produced by the agent as it interacts with the environment align well with the embedded states of the expert. And so it's both a combination of just kind of L2 distances between these latent representations, but also they're looking at the Wasserstein distance or Kantorovich distance between the distribution of the states that your trajectory observes. So your expert trajectory will have one fixed distribution of these states, but the trajectories of states that you collect when your agent is interacting with the environment might vary, and it will sort of get updated as the learning process proceeds. And so this Wasserstein distance that I said it's Kantorovich distance, if you speak to my supervisor, Prakash, my ex-supervisor, Prakash Parangaran, he gets very angry if you say Wasserstein because the original name was Kantorovich or Monge Kantorovich. But nowadays, most people know it as...
I've only heard it at Wasserstein.
Yeah, that's sort of what... I don't know. I'm not sure. I think the Wasserstein-Gann paper maybe helped make it really that name popularized. But when I was doing my PhD, I'd never heard of Wasserstein. It was all Kantorovich. Anyway, they're the same thing. There's apparently a whole book that discusses the history of this metric. But what's nice about this metric, whatever you want to call it, often it's also called Earth Mover's distance, and the reason it's really nice is because it gives you this continuous measure or distance between two probability distributions. So the high level intuition is let's say you have a hole with a particular volume, and you have a mound of dirt of exactly the same volume. And there's a cost for each grain of sand and where you put it in that hole's volume. So what you want to do is transfer all the dirt from the mound into the hole with as minimum cost as possible. And so that's kind of the way you can think of the Kantorovich or Wasserstein or Earth Mover's distance in a high level sense. So a lot of these metrics are based on this. In fact, the by simulation metric that I was talking about before is using the Kantorovich metric in its computation. Okay, so let me see if I put any other metric papers that I wanted to talk about.
Just a quick question on that one. The premise there is around this idea of state alignment or minimizing the state distance. Is that, to what extent does that impose a degree of impracticality for this kind of approach, meaning having access to both of the states? Is that an issue at all?
Well, as I said, this paper is mostly meant for the imitation learning setting, where you do have a trajectory of experts, of some expert. So if you don't have that, then yeah, I don't know if this method is applicable. Another thing that I have been interested. I'm still interested, but not actively working in this area, is when you have suboptimal experts. So a lot of this imitation learning work often assumes you have an expert instructor or a near optimal expert. But this is not always the case, right? So if you I don't know, if you think of how kids sort of learn to play video games, they watch each other playing, and they're not experts, but they kind of learn from each other, and they sort of bootstrap from each other in a sense. And so I have this paper I put on archive. I can't remember if it was this year or last year. Anyway, it was a rejected NERD submission from 2012 on exactly this idea. So if you have a set of experts or that you're trying to learn from, but they're not necessarily optimal, if you have a rank between them, then you can learn something from that. And the idea is to use sort of max margin methods, which other people have used for imitation learning, but this is a multi-max margin method. So you're trying to maximize the margin between each successive class of experts.
Okay.
So yeah, this paper, back to your original question, this paper I think is mostly applicable in this imitation learning setting.
Okay.
So one paper that is not on this list, but I'll add it later, is a paper that we was presented at the DeepRL workshop, as well as the biological inspired RL. I can't remember the exact title. It had biology and RL in the title.
That's a workshop, or that's
it was a workshop. Yeah, that was a workshop.
I did not know that workshop existed, and that there were that many papers that were looking into biological RL.
Let me just confirm that, because maybe I'm totally misremembering the title. So the first author is the one that, biological and artificial reinforcement learning. And so we presented it here, as well as so we had an oral here in the biological. So our paper, this is with Rishabh Agarwal, Marlos Machado, and Mark Belmar. Our paper is titled Contrastive Behavioral Similarity Embeddings for Generalization and Reinforcement Learning. And so this is using this idea of metrics. It's not by simulation metrics, but it's a metric that Rishabh actually came up with that's kind of inspired by simulation metrics. So in by simulation metrics, the way I like to think about them is almost like induction, right? So in induction, you have a base case, and then you have the inductive step, right? And then so you start from the base case, and then it kind of grows, and that's how you get this power. Like when you do proofs by induction, or when you write a recursive function or something like that, this is how you get that simplicity from, it's well-founded if it has a base case. So in by simulation metrics, I view it in a similar kind of way, where the base case is the difference in rewards. And then the inductive step is sort of this unfolding and looking at the next, at the probability, the transition probabilities into the next states, and how that fits in within your current metric. And that's where I won't go into the details, but that's where the Kantorovich comes in, that it's sort of spreading your current metric estimate to the next state distributions. So in this paper, the contrastive behavioral similarity embeddings, we are replacing that inductive step. So rather than looking for two states, rather than looking at their difference in rewards under all actions, we're looking at their difference in optimal policies. So let's say we have a collection of MDPs drawn from some distribution, and you can look at for two equivalent states, but from different MDPs drawn from this distribution, you can look at their optimal policies. And if their optimal policies are the same under a collection of these, then you can kind of start to think of them as being sort of equivalent, in the sense that you act the same way when you're acting optimally. And so we use this for generalization, in the sense that if we're able to use like a small set of MDPs drawing from this distribution for which we have optimal policies, and use that to learn these representations. Then when we go out of distribution, so when we sample other tasks from this distribution, these representations actually are quite meaningful and help us learn faster. And so this metric that we use, we call it policy similarity metric. It's in shape, it's very similar to the bisimulation metric, but again, what we're replacing is this difference in rewards, where we're looking at difference in optimal policies. And so then we use this metric to construct basically a new contrastive loss. And so these are we call policy similarity embeddings. And so it's a contrastive loss that in the sort of the underlying measure of similarity is this policy similarity metric that we introduced. Sorry?
How do you go about constructing a difference in policies?
So we use just total variation distance. This is in the tabular case when you can construct this exactly. In the deep setting, because we have some experiments with DeepRL, I think we're using sampling in that case. We're just basically looking at we're drawing from a replay buffer, and we look at the optimal action selections and sort of push them together when they're choosing the same actions and apart when they're not. And so we evaluated this both in a tabular setting, because then you can really compute this metric in closed form. In some simple, we're using this jumpy world domain, where I don't know if you've seen it, but it's a generalization task where it's a ground and you have an object that an agent can jump over. Mm-hmm. And so the agent has two actions: go right or jump.
Okay.
And basically you have to jump at the right point, or else you'll fall too soon and you'll hit the wall. Or if you jump too late, you won't be able to jump over the obstacle. Okay. And so you can move the floor around and move the object around. And that's where the generalization comes in. Are you able to generalize beyond the particular configuration that you've had? And so something like using data augmentation with pixels, which is what you often do for these types of problems, doesn't work very well. Especially when you start doing some adversarial things, like, for instance, color is meaningful for what you have to do. So Rishab added some interesting tasks there where the color of the obstacle indicates whether you want to crash into the obstacle or jump over it. And so these methods that use data augmentation, where you kind of perturb the image, don't work very well, because then you end up losing the critical information of the color. So we have some experiments there, but also some experiments in DeepRL. So we're using the distracting control suite. So it's the DM control, the DeepMind control suite, where you have things like Acrobat and pendulums, swing up pendulum and things like this. But in the background, so these are trained from pixels. In the background, you have videos playing that are completely unrelated. So you'll have videos of a bear moving around and things like that. And so this is really challenging if your method isn't able to handle this type of noise that's unrelated to the task. And so the method that we're proposing is actually quite effective at sort of discerning what's important. And again, it's leveraging this idea of similarity through action selection.
Mm-hmm. Okay.
So that is one paper that's using bisimulation metrics, but in a kind of a different way. So I'll mention here, it's not in this. While we're on the topic of bisimulation, it's not in this list yet, but I'll add it. So I published this paper this year at AAAI. That is essentially showing that you can approximate bisimulation metrics with deep neural networks. So before this paper, bisimulation metrics were essentially used as a theoretical tool more than anything, but it hadn't really entered into the deep network arena, because the computation is extremely difficult, and this Kantorovich or Wasserstein is a very expensive object to compute. And when you're computing bisimulation metrics, you do it in this kind of iterative fashion where you keep updating your estimate, very similar to what you do in value iteration, but in value iteration where you do the expectation of the value for the next state at each step. For the bisimulation metric, here you're doing the Kantorovich between the next state distribution. So it becomes really, really expensive. The complexity is quite large. And so what I did in that paper is I said, well, what if we assume for simplicity that we have deterministic transitions? Well, then it turns out that you no longer need to compute the Kantorovich because there's no next state distribution. And so now the update becomes very similar to what you see with value iteration. And well, we know how to handle things like value iteration with deep networks. That's basically what DQN was. Mm-hmm. And so I derived an update rule for bisimulation metrics in deterministic systems. And a mechanism for training it. So essentially you could use a replay buffer and just draw pairs of states from that. Or in fact, what I ended up doing is if you draw a batch of states, right, from your replay buffer, which is what we typically do, you can squarify that. So in the sense that you basically make it a square matrix, and then each element ij is becomes your estimate for the distance between state I and state j from the batch of sampled states. And so what's nice about this is that I was able to use it to train an estimate of the bisimulation metric for a trained agent. So another thing that I introduced in that paper that, I mean, the idea I think had already been around, but I guess I formalized it for a particular setting is what I call pi bisimulation metrics. So typically pi bisimulation metrics, yeah. Okay. So pi as in policy. Yep. Okay. So typically bisimulation metrics are policy agnostic. So when you compute them, they tell you the upper bound, the differences in optimal values, as I mentioned. Unfortunately, they don't tell you anything about any other policy, which can be problematic when you're in the learning setting because your policy is constantly changing. So if you group together states too quickly, it's not always clear that this will actually do the right thing for you. So pi bisimulation, what it does is it says, well, let's sort of modify the definition of bisimulation metrics, but for a specific policy. And so then when you do that, it solves some of the issues that I was having when trying to, for instance, use contrastive losses or actually approximate these metrics using deep networks. And the issue is that when it's policy agnostic, you have a maximization term. So what ends up happening with deep networks is that you push all the distances as far apart as possible. So you end up with this giant hypersphere where all the points are equidistant from each other. So it's completely useless at that point. Mm-hmm. But with pi bisimulation metrics, I was able to learn meaningful metrics that I evaluated on Pong and Atari and other games like this, where you see, so if you just look at pixel differences, the metrics that the distances that you see with this metric go beyond pixel differences, and they're looking more at behavior. So, for instance, if you look at if you consider the start state, what is the furthest state according to this learned distance? Well, it turns out it's the states where it's about to die, where the agent is about to die. And that sort of makes sense from a behavior point of view. But if you look at the pixel differences, they're not all that different. So that work was used by Amy Zhang. It's another paper that is not here because of the archive
criteria.
But let me look up the name because now that we have it, they put it on archive. So this is Amy Zhang, Rowan McAllister, Roberto Calandra, Yarin Gal, and Sergey Levine. And it's called Learning Invariant Representations for Reinforcement Learning Without Reconstruction. And so they're using a type of bisimulation metric here and using these contrastive losses. The way they get around the stochasticity, remember in my paper, I assume determinism, and that's how I was able to get the update. If your transitions are Gaussian, then the Wasserstein 2 metric can be expressed in closed form. So under that assumption, if you assume Gaussian transitions, then you can actually express it in this nice way, and you get this nice update rule. And so they were able to use that, which worked quite well. I won't go through all the details, but essentially, in my paper, I was basically taking a learned policy, so pi star or something close to it, and then just learning the metric on top of that. They actually used this loss to improve the representation while the agent is learning. So they were able to learn faster, and they actually used the loss from my paper as a baseline to compare against. It's something I didn't do in my paper. So it was really exciting to see it. The loss actually works for control, but they obviously obtain better results than that. And so this is really what excites me about contrastive losses. This idea of using these metrics to sort of derive in a very principled way. Not to say that the other papers aren't principled, but in a way that at least I understand better, and that gives me some grounding in terms of what it means for the underlying MDP. Using these metrics for driving the contrastive losses closer together when they should be. So dealing with stochasticity is something that I'm actually very actively working on right now, and we hopefully will have a paper we have a paper already, but it's not yet ready to be shared. But very nice theory, very nice math, and very nice experimental results as well. So we're hoping to be able to share that with people next year. So another, I don't know how much time we have if you want to switch to another topic.
So we're still in representations of metrics.
Yes.
So
maybe we could
switch to we've talked a little bit about the understanding and evaluating deep RL. Do you want to go through the highlights there?
Sure, yeah. So as I said, this is an area that I'm very, very excited about. One paper that I'll just mention briefly, we published at the Deep RL workshop with a future student of mine, Johan Samirovando Cerón. This paper, it's called Revisiting Rainbow, Promoting More Insightful and Inclusive Deep Reinforcement Learning Research. And what we're arguing in that paper is for the value that small and mid-scale environments bring to the research community. So Johan I started sort of giving him homework to kind of get him ramped up before he joins us next year for a master's. And he started doing some really interesting things, running some interesting experiments, but everything was being run on a Google Colab. So a single GPU, and he had to really be careful about what experiments he ran.
Mm-hmm.
But he started getting some really interesting results, and I said, it would be impossible for somebody like Johan to write a Rainbow paper, right? Because Rainbow was run on Atari, it was run with all these different algorithms. And so just running Atari takes like 5 days. And so we started asking ourselves, well, what if we redid the Atari experiment, but with these small and mid-scale environments? And we did that, and we end up coming to the same conclusions as Rainbow, that basically all the algorithmic components are best when mixed together. But we also discovered some really interesting results that I won't go into too many details here, but that made us realize that these interesting results, I don't think they realized them when they were initially developing the Rainbow paper, because these types of experiments are so expensive to run on Atari that you have to be more selective as to what you run. But if you're running on something like Cartpool or Acrobat that take 10 minutes to run, you can really start asking a lot of questions. And of course, not everything carries through directly to Atari, especially because Cartpool and Acrobat typically don't use convnets. But then there's these other environments like Minotaur, it's a miniaturized version of some Atari games. And so these do have convnets. And so you can start sort of ramping up. So for instance, one thing we discovered is that distributional reinforcement learning, when you add it on its own to DQN, doesn't work very well if you don't have convnets, which is really surprising to me. And it's something we're still digging into. So what we're arguing is that researchers should not basically discredit or be dismissive of small to mid-scale environments, that they actually provide great scientific value because you can do really large sweeps and ask a bunch of questions. Like, for instance, another thing we discovered is Huber loss, which is what DQN uses. And that's what everybody uses nowadays, because if you build on DQN, because that's sort of what was used in the original paper, if you've switched to Atom, which a lot of people have lately, it turns out that it's better to use mean squared error loss. And so this is just something that people don't question that much, and which is fine. I mean, you still get reasonable performance with Huber, but you get much better with mean squared error. And so these are the types of questions and answers you can get with these smaller systems, and then maybe start when you get something insightful like this, see in the larger environments.
And was that discovered because you were looking for that result or those kinds of results, or because you were able to just try a lot more and found things that worked more easily because of that?
So the Huber loss versus MSE, that was actually found by Johan, and it was when he wasn't looking for it. He was just asking questions, and when he was implementing things, I mean, he was sort of ramping up in reinforcement learning at the time, and in our meeting, one of our meetings, he came to me and he said, "Hey, I wasn't sure. I hadn't implemented Huber loss, and it was just easier to implement mean squared error. So I ran it. But then after I implemented Huber loss, it seems mean squared error works better. Why?" And I was like, "I don't know. I actually don't know why." And so then that's sort of where the idea started coming from. It's like, well, that's quite interesting. And we ran it in a bunch of other environments, and we saw that it held throughout all of them. And I was like, okay, this is quite cool. I ran it on some Atari experiments, and it holds there as well. But it holds with Atom, not with RMS prop, which was the original optimizer that DQN used in their paper. So if you look at RMS prop and Huber versus MSE, Huber ends up winning. So now you understand why DQN
results are linked. The Atom and the MSE are linked results.
Exactly. And so these are the types of questions that we typically don't ask ourselves when we're running these large scale environments. Like, you say, okay, I'm going to switch to Atom because that's what people seem to be doing nowadays. But as we see, it has some effect on how it interacts with other components. Another thing we found that was super surprising is Rainbow uses C51, which was the original algorithm of distributional RL. But that's just one way of parameterizing your distribution. Quantile regression is another way, and so we experimented with that. And so it turns out that quantile doesn't work well with dueling networks, which was really surprising because in the paper itself, they say it should work with dueling networks. And so it's something we're still digging into. But again, I think there's a lot of interactions that we sort of take for granted that you can't always necessarily just swap one thing for another or add something new and have it kind of add value in isolation. Like there may be some interaction with some other component that we just don't understand yet. And so this is the line of work that I'm particularly excited about in getting these understandings and improving our knowledge on this space.
In addition to the kind of inclusion element of the benchmarks being just so expensive to run, it's also you're starting to ask this question around, are we just over indexing on the benchmark, that we've been asking about ImageNet and all the stuff that's happening in computer vision, but for RL now?
Yes, exactly. So again, one of the seeds for this work was the realization that despite Johan was doing an excellent job coding all of these things and sort of asking the right questions, there was no way he could have done Rainbow with a single GPU. Like now, because we're using JAX, we were able to get him some TPUs and cloud. So he's been using that, but they're not that many still. Like definitely not enough to run a full Rainbow paper worth of work in a reasonable amount of time. So that's unfortunate, right? Because if you're from a place with that's underserved in terms of resources, either you have to do hard theory, or you kind of have to pick a different area. But if deep RL is really what you're interested in, or what you did your PhD in, and you're trying to build a lab on that, it's going to be really hard if everybody is always demanding larger experiments and sort of discounting these small to mid-scale experiments. So what we're arguing here in this paper is as a reviewer, don't be dismissive. You can do good science with these small environments, and if that's the case, then great. And it also means that people without access to large compute can also participate.
Yeah, I'm wondering if there are analogs, or the extent to which there are analogs or known analogs in the language model space. Like, I think the same realization has been happening in the language model world, where we're training these 3 billion parameter models, and if you're not affiliated with a very well-heeled lab or company, it's very hard to compete in that kind of research. And so you see folks kind of trending more towards, or shifting to, like, theoretical, like you said, or more applied, applications of language models. This kind of an analog to this result in that world would be, well, you can still learn some of the same fundamental things from smaller language models. I don't know if that exists or not.
Yeah, that's an interesting question. I probably don't know the language model space as well as I should to really be able to comment in depth. But I think probably one of the things that makes it a little different and a little more challenging in the language model space is that there's an underlying structure that you can't get away from, which is language, right? Mm-hmm. So you can imagine coming up with a made-up language that's very small. And so there are certain types of questions you can ask and get answered in those types of scenarios. But ultimately, I mean, what most of the researchers in that space are interested in is in representing real language, be it English or for translation or whatever. And so when you shift to these small models, well, then you have the difficulty of how representative is it of real language and of grammars and things like that. So it's an interesting question, but I think perhaps one advantage we have in RL is that it doesn't really have that kind of underlying structure for the types of problems we run. I mean, so like a 4-state grid world is totally fair game if that sort of helps highlight whatever contribution you're making. Yeah. Which I think would be more difficult in the NLP space. Okay, so let's go to some other papers. So one that I liked, this was iClear, was by some colleagues. It's called Measuring the Reliability of Reinforcement Learning Algorithms, by Stephanie Chan, Samuel Fishman, Anup Koratikara, John Canny, and Sergio Guadarrama, sorry. And here they're looking at deep RL, and they're looking at a few different metrics that they introduce to evaluate the performance of these algorithms beyond just, is my curve higher than yours, and did it reach that high point faster than yours? Mm-hmm. So that's a fine metric, but I think there's more we can ask of these algorithms. So what does it mean if you reach a score higher? Like, the shape is fine, but how risk averse are you? How sensitive to risk are you? How stable are you across runs? This is something that has been already discussed quite a bit in the past few years. Mm-hmm. The stability of algorithms across different runs, especially because when you're running with really large environments, that's another issue. Another advantage of running smaller scale environments, you can run a ton of independent runs and get much tighter, more meaningful confidence intervals than you can with something like Atari. So that's a really nice paper that I like quite a lot. And so they have some pretty broad analyses of existing algorithms and how they perform relative to each other across these different rubrics. So they look at value-based methods, which are the ones I mostly look at, as well as method policy gradient methods. So very nice paper. Another paper by other colleagues, a lot of them in Montreal with us, is the Revisiting Fundamentals of Experience Replay. This was presented at ICML. So this was by Liam Fetus, Prajit Ramachandran, Rishabh Agarwal, Yoshua Benjo, Hugo Larochelle, Mark Rowland, and Will Dabney. And here, this is very much in the spirit of what I'm excited about, and looking at the things that we kind of take for granted when we do deep RL research, like the replay buffer. What does it mean to change the size of the replay buffer? What does it mean? Like, how is your training affected when you change how old the latest policy in your replay buffer is? And so they introduced these terms like the replay ratio, which relates to how often you update your replay buffer, how big your replay buffer is, and how this ratio affects the learning process. So I really like this type of work because it's I think there's less of an emphasis now, but I feel like 2019 there was, and 18 perhaps, there's still a bit of this, but a lot of desire to get state of the art. So you want SOTA, and reviewers want SOTA. And so if you have a paper that isn't SOTA, then why are you publishing it? And I think that's not a great take on these types of papers. I'm glad this paper was accepted because I really think we need to take a more critical eye into the different components that of these systems we're using. They're very complex. They include a whole bunch of different things. And it's easy to sort of take it for granted and say, I'm just going to focus on this one part, which is what I'm working on. But as I said before, like there may be some strange interactions with other aspects of the DeepRL, the overall DeepRL algorithm that you're using that are important to understand. And so I think along those lines, the next paper I wanted to talk about.
Quick question on that last one. Were they running their own experiments, or was this a review of published results and looking at, I guess the question that I'm asking myself is, are these like replay buffer hyperparameters, are they even regularly published with results, or, is that, part of these, like what we talked about with VAEs, like things that people tune and don't really talk about?
I think, especially more and more nowadays, people do publish their hyperparameters. So with these checklists where you have to specify whether you're including code and what your hyperparameters are, at least I do check. And I think a lot of other reviewers do check as well, which is a great thing because there's nothing more frustrating than if you're a student and you're trying to reproduce a paper and you've implemented it as far as you can tell word for word and it doesn't work, and then it turns out that the authors forgot to include a very critical hyperparameter. That's extremely frustrating. So for this paper, they reran their experiments. So they implemented all their code, and so they're using some setups that I don't think have been published before. And so that's the type of question they're asking. Like, if you were to do this, what does that mean? And so I think it's a great paper because if you're starting to play with the replay buffer and perhaps use its design and size and all of that, trying to use it to your advantage, I think this paper is really useful in terms of understanding what are likely the dimensions along which you'll get the better bang for your buck.
Let's maybe, if you've got another paper you want to cover in this understanding thing briefly.
Just one more. I wanted to mention the behavior suite for reinforcement learning, or B suite.
Yep.
This, I won't go through the authors, a bunch of DeepMind authors. Ian Osmond is the first author. This paper is not specific to DeepRL, but it's really trying to look at what they call core capabilities of reinforcement learning. So they're looking at exploration, credit assignment, generalization, memory, noise, scale, things like that. And so they have a bunch of small environments along which you can evaluate your algorithm, as well as some larger ones. And I just really like this type of work because it's again, taking a critical eye to these algorithms and going beyond just reported training performance, which is when you're searching for SOTA, that's often what you end up looking for. And this is really looking along all of these different rubrics. How do you perform? And it's unlikely any algorithm will perform best along all those rubrics, but at least you get a better idea for if you're really focused on exploration, did that mean that you really had to sacrifice robustness to noise or something like that? Not necessarily that means that your paper should be rejected, but it lends a better understanding to people that may want to use your algorithm in the future.
You've got in your notes example of one of the radar charts that they published in the paper, and it's a great way to represent the relative results here.
Yeah, I think it's that's another thing I really liked about this paper, the way they visualized it, because there's all these dimensions.
Yeah,
so it's difficult to come up with. I really enjoyed this radar plot. It's really nice.
Yeah. Cool. And so I want to make sure that we cover some of the real world observations that you've made, because that's something that I've been tracking for the past few years. And I think without fail, we're starting to see more and more interesting examples of RL, peeking into the real world. So I'm curious to see what you've come up with in your review.
Yeah. So here it's a little more self-centered. The two papers that I'm considering are an author on both. But again, I think this is more a consequence of my lack of visibility of work in this area, because it's not most of the work where I'm doing like literature review and sort of scouring papers is along the two groupings that we mentioned, that we've already been discussing. So I know there is some work in recommender systems. There's a team at Google actually that's doing a lot of work in reinforcement learning for that, and they come up with open source code and benchmarks for that. I think they're even using dopamine for part of it. I know the Royal Bank of Canada actually has a whole team that does reinforcement learning. Matthew Taylor's now it's I think part of Borealis AI. But when I spoke to him, he told me that they were actually starting to use reinforcement learning in real public-facing settings. I don't know the details, but that's encouraging to hear. And so the two papers I chose for this, the first one is one that we presented at the Machine Learning for Economic Policy workshop at NERPS. It actually won Best Paper at that workshop, and it's basically. It's a long title. Let me look it up before I mess it up. Estimating policy functions and payment systems using RL. So this is a collaboration I have with the Bank of Canada. And so the Bank of Canada is kind of like the federal bank. So they're not in it to make money. They're really there as a regulatory agency. And so banks in Canada need to send payments to each other. So this is just kind of natural dynamics of different customers having different bank accounts and that type of thing. And so at the beginning of each day, each bank will request a certain amount of liquidity from the Bank of Canada. And this is so that they can meet the initial payments that they'll receive without delaying them. Because if they don't have enough liquidity to make their payments, they have to delay those payments, which incurs a cost. So they'll receive payments that they have to make during the day, but they'll also get paid by other banks. And so that helps them increase their liquidity. So it's almost like a bandit problem, you can think of this initial liquidity request, because they have to sort of try to anticipate how many payments am I going to receive and at what point, and what are the payments I'm going to have to make. And so that selection is quite complex. You can't obviously request as much liquidity as you want, because there's a cost to it.
Yeah. And
so then at each time step, if you delay payments, then there's a cost to that. And at the end of the day, you have to make all your payments. If you don't have liquidity at that point, you have to borrow from the Bank of Canada, and there's a higher cost to doing that. So this is kind of the problem that these different banks face. And it's a multi-agent system, because you have multiple banks that are sort of trying to optimize these things for themselves. And then you have the Bank of Canada as sort of the central regulator that's not really playing the game. It's more just kind of loaning money and ensuring everything flows smoothly. And so the Bank of Canada is interested in understanding this dynamic better. And so what we're exploring in this paper is, can we use reinforcement learning to do just that? So when you simplify this setting to a very simple two-party system with a single time step, you can solve the optimal solution, the Nash equilibrium of this in closed form. So that's what the economists did. They solved what's the optimal amount to request from the bank at the initial liquidity. And so then that was our initial step. Let's see if we can train RL to sort of find this analytical solution, and we were able to do it. So that was kind of an initial proof of concept of, okay, it actually can do the right thing.
Mm-hmm.
And so what we're doing in this paper is, first we're separating the initial liquidity problem, which is kind of like a bandit problem, but in a more complex setting. So not just the simplified scenario that I mentioned. So in the more complex setting, we don't have the closed form solution. So we're more looking at how the cost evolves over time and the loss that we're learning, that type of thing. And then also the second aspect that we sort of separated from the initial liquidity is how much payment to send at each time step, right? So if you send all your payment, then you might run out of money too soon. If you don't send enough, then you're going to incur delay costs. And again, this was able to learn quite effectively. We don't have a closed form solution to that, so it's more based on sort of the analyses that the bank typically does for this type of thing. And again, this is a multi-agent system, so it's not a single RL agent learning everything. We have two RL agents that are sort of co-learning. And so this is quite interesting because the dynamics of multi-agent systems are very difficult to understand and anticipate. And so this is quite promising because it shows that we can start thinking of these machine learning tools as mechanisms for getting a better understanding of these complex dynamical systems that we're already affected by today.
In this setting, is there any kind of constraint on the total capital in the system or that the central bank has access to?
No, you typically assume the central bank has as much money as you need.
Yeah, I would think that, from a real world perspective, which I guess is what we're talking about, yes. The question came from, thinking about this as a general, as an example of like a game theoretical application of RL, where you tend to have these interactions between the behavior of one agent and the behavior and outcomes of other agents.
Yeah, so there is definitely a big game theory component to this work. Some of the, like Rodney Garrett and Francisco, they do a lot of that type of research. So I think there's beyond just banks. I think that this type of work, it will find that what the findings will carry over to kind of more theoretical or more academic research in multi-agent RL, the types of dynamics we find. And so to continue along those lines, I didn't put this paper yet here, but another paper, so 3 papers that I'm on. The other one, this was actually presented was an oral at the creativity workshop at NeurIPS. And here we're using multi-agent RL to train these little agents in a dynamic film is what they're calling it. So it's a film, it's a VR, it's meant to be VR, but you can view it on your phone as well. It's called Agents. So if you go to agents.ai, you can download it and it's really fun to play. But the premise is you have this planet that has its own gravity, but it's also kind of in this void that has its own gravity. So if you fall off the planet, you're going to fall into the void. And so you have these 5 agents that are sort of walking around. Yeah. And if they move over to the side of the planet starts tilting, and so they might fall out. So they have to kind of learn to balance each other and between the 5 of them to sort of balance the planet so that it doesn't tilt over and they don't die. And then as a user, the reason it's called a dynamic or interactive film, as the user, you can come and you can plant this little tree thing in the planet. And the agents are drawn to this tree and they want to sort of consume the fruit. And as the tree grows, it also has its own mass. So it's going to tilt the planet in a particular way. And so we use multi-agent RL basically to train these different agents to have their own behaviors. But this is all affected by where you place the tree, how many trees you place, etc. And you can also, they have some scripted agents that don't use reinforcement learning. And so you can choose which ones have RL and which ones don't. And so that creates a whole different dynamic. And so here the purpose is really just creative. We want something that's compelling and has a nice narrative to it. And it worked really, really well. So yeah, they're still working on it. And sorry?
Agents.ai?
Agents.ai, yeah, AGENCE. It's a play on RL agents. So it's really cool. And even though it's not like banks or flying balloons or anything. I still find it real world because it's something that people are interacting with when they play with this game, and it's affecting their emotional state or whatever, because it's RL that's actually affecting the game dynamics and the narrative that ends up coming out of this experience.
Yeah.
So I found that really cool. And again, it's another exploration that I'm making into this multi-agent RL space.
Mm-hmm. Mm-hmm. And speaking of flying balloons,
yes. So then the big paper for us this year was a Nature paper that we published, was announced 2 weeks ago.
Long ago.
Sorry?
I just said not too long ago.
No. So we knew it was already accepted like over a month ago, but we couldn't say anything until it was fully out.
Yep.
So it's called Autonomous Navigation of Stratospheric Balloons Using Reinforcement Learning. So here, this was a partnership with Loon. So Loon is a Alphabet company. It used to be part of Google X. And you may recognize them. What they do is they make these giant balloons that fly in the stratosphere and bring internet basically to areas with no connectivity. And so they have these balloons flying over Kenya and Peru and really bringing internet to remote areas where they use it for their livelihood. And so it's a really a problem that's really important and could really bring a lot of good to the world. I think after the I don't know if the most recent, but one of the most recent hurricanes in Puerto Rico, they were able to use these Loon balloons to help give people connectivity because everything had been sort of destroyed. So there's many very, very challenging problems in the space, from like building the balloons to testing the robustness of the balloons to launching them and then obviously controlling them. Mm-hmm. And so Sal Candido, the CTO of Loon, gave a great expo talk at NeurIPS. The recording is probably still available, but he does a really good job of sort of giving an overview of all the different complexities there are in flying these things. So the way you control these balloons is by basically surfing winds. So in the stratosphere, you have different layers of winds at different altitudes. So the stratosphere is probably going to get this wrong. I think it starts at like 12,000 feet or something above. No, I'm totally getting it wrong. We know it in pressures, in units of pressure. I think it's 14,000 units of pressure, the barometric pressure. And so the way it works is that these winds kind of flow in one direction at one altitude and then flow in a different direction at a different altitude. Yeah. And this changes over time. So Mark Belmar also gave who's the first author of this, gave a talk at the Deep RL workshop. He was one of the keynotes. And he went really into the details of the RL. So it's another great talk if you can check it out. But there, one of the images he has is the wind patterns in the tropics over from 1960, I think, until now. And you can see there's some regular patterns every 10 years, but they're constantly changing. Okay. And so the way you fly these balloons is by going up, down, or staying. So if you stay, the balloon is going to drift with the wind. But if your wind is drifting this way and you want to go the other way, then if you have an idea that the winds are going in that direction in a higher altitude, then you're going to want to bring the balloon up and then it'll come back. And so it's kind of challenging because you have to both sort of figure out how to navigate these winds, and you also have to have an idea for where the winds are going to be at different altitudes. So there's partial observability here because we have some forecasting mechanisms, but they're obviously not perfect. And then you have to deal with power. It's a solar powered balloon, so at night you can run out of power very quickly. So a lot of challenging problems. And the one we were tackling with this paper is what's called station keeping. So if you have a particular point on the Earth where you want the balloon to be delivering internet, then you want the balloon to stay there. But because it's sort of floating in winds, you can't just say stop because the balloon will drift it away. So it has to kind of do this funky figure 8 pattern where it sort of navigates the balloon and the altitudes to try to stay within a 50-kilometer radius, which is what we want to be able to deliver that signal there. And that's a very challenging problem. And they had a static controller that a bunch of people with PhDs in like dynamical systems and understanding winds and aeronautics and things came up with. And so we developed this reinforcement learning agent that was trained using these wins, and it was able to surpass the performance of the station keeping agent in terms of staying within that area. And so obviously this was all trained in simulation, and we have a big production pipeline to train these things that the Loon team had built up. But what was really exciting is when we started trying these things out for real in the world. So deploying these controllers and balloons in the world, and when they actually were doing what they were meant to be doing, that was just incredible, because it's like, wow, they're actually doing it. You hear about the sim to real problem, which is a very important problem. It's a very challenging problem, and we were able to sort of navigate that gap pretty well, in the sense that the agents that we train in simulation were able to handle the real world quite well. And so this was extremely exciting. And
Did you particularly design for that, meaning domain adaptation techniques, or specific techniques to inject noise in your data, or things like that, or did it just transfer well to the real world?
No, I mean, there were a lot of, it wasn't like we just plugged RL in it and it worked. There was obviously a lot of design decisions we had to make along the way to make it work well. So during training, we had mechanisms of doing something akin to out of distribution evaluation. So we could train in a particular setting and then evaluate it with a different, it could be something as simple as same location, but just a different year. And the wins would be very different. And obviously trying at different locations and things like that. And that's how we sort of started building up confidence in our controller. And so also, like, dealing with the partial observability during training helped the agent be more robust to the real partial observability in the real world. So a lot of these things, I mean, when it started being deployed in the real world, it wasn't like the first agent that was deployed is the one that's flying now. We kept on iterating and improving on it. But it's flying a bunch of balloons now.
Interesting. Yeah, when you first mentioned this, the obvious thought was, sounds like a classical control type of problem. And you mentioned that it outperforms. What does outperform mean in this context?
So the main metric we're using is time within radius.
Okay.
So if you evaluate this over like a day or 2 days or a week or whatever, you want to make sure that you're getting more time within that radius. But the other metric that we're using and so we have in the paper these Pareto plots that have I can't remember what was in the x-axis. So I think let's say time within radius in the x-axis, right? So you want this to be further to the right. And then on the y-axis, we have power consumption. So we want to be within radius without blowing out the power, because at night, then if you blow out your power, then you can't do anything. You're stuck at drifting. And so you can get this sort of Pareto, this Pareto frontier that, and we did this in simulation by doing like really expensive rollouts that you can't realistically do in the real world, to get a pretty good estimate of what this frontier looks like. And so with this type of analysis, we were also able to see that, and you can see it's really neat when you see it through training. You can see our controller, the more you train, the more it sort of starts approaching that frontier. And so it gets a better trade-off of time within ratio and power consumption than the static controller. And then there's a whole bunch of other analyses we've done as well that sort of convinces that it's doing a better job.
Cool. Let us transition to a few lightning round questions to get us closed out. I think we've covered the main topics we wanted to cover: generalization, understanding and evaluating, and RL in the real world. Thoughts on the most interesting new either tools, simulation environments, open source projects. 30 seconds to list the ones that come to mind.
So I would say the one for me that I'm most excited about is JAX. And this isn't specific to RL, but we use it in RL. So Dopamine now has it. And I think it's just a really, really beautiful ecosystem. It has a lot of the advantages of TensorFlow in terms of speed and that type of thing. But it tries to make it in a way that seems like you're writing NumPy. So it's very intuitive and very easy to kind of get into. Yeah, I've been using it now for my research exclusively, and DeepMind has Relax, and there's a bunch of other libraries that are building on top of that. So I think that for me is my favorite one of 2020.
Mm-hmm. And what is the thing that it displaces in your toolbox?
TensorFlow. So I now build my agents using JAX.
Okay.
Yeah.
Cool. And any others? Any others that come to mind?
So I think there's more. Well, B Suite that I mentioned earlier. So that suite I think is really nice because it again allows you to evaluate your agents across a variety of important rubrics. I think there's been quite a bit of work, although I'm not as familiar with the space as to know if it was all in 2020, but there's quite a bit of work in procedural generation of environments, which I think is kind of interesting and exciting, especially as we talk about generalization and that type of thing. I think being able to have the ability to programmatically generate out of distribution examples is quite neat. So Matt Budvinick gave another keynote at the DeepRL workshop, and he was talking about a similar idea. They're building a system called Alchemy, I think. I don't know if it's open source yet, but that type of work I think is quite exciting.
Okay. And then spending a few minutes kind of looking forward into 2021. Thoughts on kind of the most exciting opportunities for RL? Where do you think the puck is going to go? To use something that a Canadian would understand.
I always struggle with these prediction things because I always get them wrong. I think there is going to be more and more work in really dissecting DeepRL in the spirit of what I was mentioning before. Mm-hmm. We're already starting to see some of that, but I think there will be more of that. And I think this will lead to some eyebrow-raising surprises in terms of how certain things we take for granted actually behave under different circumstances. And who knows, that might lead also to a new state-of-the-art agent that is able to incorporate these things properly. The thing I mentioned with Atom and RMS prop, I mean, I don't know enough about optimizers to really be able to know if this is a sane thing to say, but I don't know, why couldn't we have an RL-specific optimizer that doesn't have this issue with that we can see with RMS prop versus Atom and Hooper versus MSE. Like, what if the optimizer were tied to whatever loss you were using, and how can we make this in a way that is natural to sort of define what the best optimizer would be? And again, I think part of the reason why I picked these groupings is because this is what I feel is going to be, for me, most exciting for next year. So seeing more deployments in the real world. Another thing that I didn't mention here, but that I am quite interested in, is getting a better understanding of the relationship between value-based and policy-based methods. So Marlos Machado, Dibio Ghosh, and Nicolas Leroux, Dibio was the first author. They had a NeurIPS paper where they're looking at the at policy gradient methods from an operator perspective, which is how we traditionally look at value-based methods, which this operator we apply. And I think that's really exciting work. I'm actually working with them a little bit now. And I'm really looking forward to understanding this dynamic better. So if anything, I hope that we can reach a point where we can say, I have this problem. Should I use value-based or policy-based method? That goes beyond what's my favorite framework. What do they provide?
Mm-hmm. And are there things that you saw that kind of as just blips on the radar or emerging trends that you see growing in importance, maybe not, in 1 year, but in 3 to 5?
Yeah, I think upending the traditional way of doing RL. There was a really interesting paper that I saw that I had in my list of others that I'll just briefly mention. It's called, this was an ICML paper, I think. Decentralized reinforcement learning, global decision making via local economic transactions. And so the way they do this work is that rather than having an agent that picks different actions, you can imagine at each point picks one of the available actions. You can imagine having multiple agents, each kind of controlling their own action, and they bid in an auction. And so then the winner of that auction gets to pick the action. And so they have some nice theory there that shows that this actually leads to good behavior. But this way of sort of shifting the way that we look at this, the dynamics of action selection, I think is really, really interesting. When I started at Google, I worked in ads. So they're using a Victory auction, which is what we were using in ads. And so that for me, it was also just really interesting to see Victory auction in an RL paper that I never anticipated I'd see. Gargalineo had this paper, I'm forgetting with whom, I think he was the first author, where he's basically arguing that the squared Bellman error is broken. And he proposes this new Bellman error that has better theoretical properties and just works better. And again, that's sort of questioning the traditional things that we take for granted when we do RL. And it goes similar in spirit to what I was mentioning before, but when I was mentioning earlier, it was more tied to deep RL. And I think there's interesting work that's looking at really the foundations of RL before you even get to deep networks.
Awesome. Well, I feel like, I know that I could continue on talking about this stuff, but I want to be respectful of your time and our audience.
My kids are going to storm in soon, so it's probably a good point to end.
Your cat's...
Yeah, the cat. My dog is actually outside. I have to go let him in. Let her in.
But Pablo, thanks so much for taking the time to share. First of all, to pull all this stuff together. Great review. And to come on and share it with us. Very, very interesting stuff.
Thanks, Sam. It was always a pleasure to talk with you. This is great.
Same here. Thank you.
All right.